Continuing our discussion in this class, please look at the diagram. As the holes, as the electrons from the n side diffuse into the p side and the holes from the p side diffuse onto the n side, so you find that some space charge is developed here as we discussed in the last class. Now what this space charge does is it prevents further diffusion of the charged particles into the other region. For instance, on the n side here we have high electron concentration. Adjacent to that we have the positive charge, okay, immobile positive charge, space charge, and by the side of that we have negative charge here, immobile negative charge in the depletion region. This negative charge prevents further diffusion of electrons from the n side into the p side. Similarly, the positive charge on the n side prevents further diffusion of holes from the p side into the n side. So there is an equilibrium that is struck with the charge opposing the movement of the mobile charge and the diffusion acting against this opposing force. So at some point of time there is a diffusion after some amount of diffusion an equilibrium is struck and no further diffusion takes place. So the current would be 0 across this junction. The current goes down to 0. So initially there is a transfer of charge and after that it goes down to 0. But what happens to the minority carriers? So you have, for example, the electrons on the p side and the holes on the n side which are minority in number, and these minority charge carriers on the other hand so can get influenced and by an external field and they can move. There is no problem, nothing prevents them from the motion. Now by means of some good metallic contacts and taking care that this one doesn't act like this kind of junction again, and applying a kind of reverse potential, that means a negative potential to p side and some positive potential to the n side. When you apply this kind of potential, let us see what happens. The n side being positively charged, so this bias, external potential elevates the potential of the positive charge on this side further. Similarly here with respect to this the negative charge on the p side goes down in potential by means of the external bias. So because of this, this space charge region further extends. The space charge region further extends because the potential barrier is further increasing. It is barrier for, so this potential difference across the junction is a barrier for the diffusion of the charged particles, majority charged particles. That means for the diffusion of electrons to diffuse into the p side and the holes to diffuse into n side. This one acts like a barrier, opposing force. Barrier means opposing force. Because of that, so no diffusion takes place, and as a result no appreciable current conducts. Okay, but if you look at the minority carriers which is small in number like this, for example electrons on this side and holes on this side, it is a field favoring their movement. Therefore the electrons do drift, not diffuse, but the minority electrons from the p side do drift into the n side here, and the minority holes from this side do diffuse into the p side here. So since the positive charge is going in this direction, there would be some current flowing in this direction, which is the some current due to the minority carriers on this side as well as on this side. And what would be the amount of current? Because it involves the movement of minority carriers and number of them are available is very small, therefore the current is very small. So when you apply this kind of a potential, which is known as a reverse potential, so there is a small amount of conduction that takes place, and which is primarily due to the minority carriers. So under sufficiently large amount of this voltage, so this current is known as the minority carrier current, and it almost remains constant irrespective of the voltage beyond certain voltage level, because the number of charge carriers is constant, and even if you increase the potential, so there won't be an appreciable change in the number of them crossing the junction every second. Okay, so this is what happens when you have the reverse potential applied. Now, if you look at the volt ampere characteristics of this device for reverse potential, by representing the voltage on the x-axis and current on the y-axis, with negative voltage, with increased negative voltage, the current is almost constant. So it will be a negative current, it's almost constant. So this is the kind of characteristics you get. With increased reverse voltage, first the minority carrier current increases slightly, but after that the current remains almost constant at this value. Let me represent it as I naught. Looking at this diagram, you understand that now I have applied positive potential to the P side and negative potential to the N side with respect to the ground, or with respect to the N side I made the P side positive biased. This is known as a forward bias for the diode, for the PN junction diode. Now what happens in this situation? The positive potential that is applied to the P side elevates its potential compared to the N side, tries to elevate it compared to the N side, and you have here the space charge which is already present. So if the influence of the space charge is like this, look at this side, if the influence at this junction, if the influence of the space charge is something like this, it's creating a say field like of this type across the junction. For a positive charge, that is a hole, so there is a barrier like this. Now by elevating the potential on this side, so what we are trying to do is we are elevating the potential of this side, and we are reducing the barrier by connecting the negative terminal to this side. Because of that, the positive particle, the hole, finds a smaller barrier than this, assuming that the voltage is small. It finds a smaller barrier than what it was earlier, and because of this reason, further diffusion of the holes into the N side that takes place. So the holes jump into the N side because of the diffusion, and by jumping the holes, it doesn't create an additional space charge because the circuit is completed through a cell, and the cell continuously supplies the charge, and as a result no further increase in the barrier takes place. Hence continuously the holes keeping diffuse into the N side and the electrons diffuse into the P side. and they being the majority carriers, a good amount of current flows in this direction, because current is defined as the charge of a charge per second and a charge rate in the positive charge rate actually. So therefore appreciable amount of current flows through the junction and through the circuit. Now if the potential is slightly increased further, the barrier is further reduced and the diffusion increases and more amount of current flows. Okay, so this is what happens, and if you look at the characteristics of the PN junction, so you will find that the current increases in this fashion. Current increases exponentially against voltage. As voltage increases, current increases, and this time with positive voltage you have positive current going into it. So this kind of biasing is known as forward biasing, because the junction is biased in the forward direction. Now it can be shown that the equation for current that is flowing through the diode can be expressed in this form. It is exponential. I is equal to I naught into e to the power of V by Vt minus 1, where V is the forward voltage, and an expression for Vt is as follows. Vt is related to temperature, and it is given by the absolute temperature divided by 11,600. So naturally the units are volts. This is about 26 millivolts at 300 degrees Kelvins. And please note that when V is much larger than Vt, so this expression is simply I is approximately equal to I naught into e to the power of V by Vt. So this 1 is negligible compared to this term when V is much larger than Vt. Therefore it can be expressed in this form I naught e to the power of V by Vt, which is an exponential function. Okay. Therefore with voltage the current rises exponentially, and when V is negative, so please note that, and when V is negative and much larger than Vt, I is approximately equal to minus I naught. There was a mistake in this expression which I have given earlier. It is not e to the power of V by Vt, but it is e to the power of V by eta Vt, and eta is 2 for silicon, eta is equal to 2 for silicon, and eta is equal to 1 for germanium. Okay, and Vt is independent of the semiconducting material. So it is proportional to the absolute temperature, and there is a constant proportional to constant which is equal to 1 by 11,600. Well, coming back to the expression, the diode current under high reverse potential, that means when V is much greater than Vt, minus V is much greater than Vt, we have I is equal to minus I naught. Okay. So therefore there is a small amount of reverse current that takes place, and since the material is saturated of the charged particles and the current saturates here, so it is known as reverse saturation current. I naught is known as reverse saturation current. Okay. Now, if you consider silicon, you will find that the volt ampere characteristics on the positive side is like this. The current is almost 0 and very small, below about 0.6 volts of voltage, and above 0.6 volts, so it rises exponentially and with appreciable amount of current. So by the time it is about 0.65 volts, you will have a huge current flowing. On the other hand, the germanium diodes exhibit a characteristics of this type with, so the voltage that which is known as the cut-in voltage is about 0.2 volts or 0.1 to 0.2 volts. So below which the current is negligibly small, and above this voltage it is appreciable. So this voltage is known as cut-in voltage, and this cut-in voltage is about 0.1 to 0.2 volts in the case of germanium diode, and this is 0.5 to 0.6 volts in the case of silicon diodes. Okay, but please note that it is a continuous curve. It increases continuously, and because of the term -1 there, so it is negligible below this and it becomes appreciable above this value. Now, as the current increases by means of the external voltage application, say in the forward direction like this, appreciable amount of current flows across the junction. And now, if the bulk semiconducting material exhibits some amount of resistance, which is true, because of that there would be some voltage, so that drops across the bulk material, and some voltage that drops across the junction. Therefore, the external voltage that is applied is equal to the bulk voltage drop plus the junction potential. Okay, and because of that reason, you have a slight increase in the voltage with increased current across the diode. Ideally, it would have been like this. The rise in current would have been like this. So beyond certain voltage, a huge amount of current flows across the junction, and this is the way the current should have risen. But that is not true because of the some amount of potential being required for reducing the barrier to increase that current, and some amount of voltage drop across the bulk semiconductor. Now let us look at the reverse side. When reverse potential is applied and the reverse potential is increased up to certain level, so what happens is a phenomenon known as breakdown, avalanche breakdown or Zener breakdown. So one of them occurs, and the characteristics of the diode would be like this. So at certain potential known as the Zener potential, a diode breaks down, the diode breaks down, and as a result you have high amount of reverse current that flows across this. And how does it take place? Because of two phenomena. When it is reverse biased, look at this diagram, when the junction is reverse biased, because of the high potential here, so the potential gradient is very high because of the charged particles. It is like a parallel plate capacitor. Because of the charged particles, there is a high amount of potential difference, and as a result high amount of field is present from the positive charge to the negative charge, and this field accelerates the minority carriers down the potential value. Okay, so for instance this hole gets attracted by the negative charge over here, and they accelerate into the p side, and while doing so they bombard with the atoms and they break the covalent bonds. So when they break the covalent bonds, the electrons which are responsible for the covalent bond formation, so go out of the covalent bond, and a whole electron pair, a free whole electron pairs occur, and these free whole electron pairs also get imparted some energy because of the bombardment and the potential gradient, and they in turn break some more covalent bonds, and like chain reaction, so there may be multiplication of there would be multiplication of the whole electron pairs that take place, and because of this suddenly there would be a large number of whole electron pairs, and they give rise to a huge amount of current. So this is known as avalanche multiplication, and the phenomenon is known as avalanche breakdown, because of which there would be a large amount of current that is flowing. With very small increase in voltage, millivolts of increase in voltage, you have huge amount of current that flows. As an example, if assuming that look at this diagram, assuming that this voltage is say 5 volts, at 5 volts the avalanche multiplication takes place, and if you increase it by say 10 millivolts and make it 5.01 volts, the current may be of the order of 100 milliamperes. So this may be very small, like nanoamperes earlier, and then that jumps to say 100 milliamperes by increasing a few millivolts of reverse potential, or by increasing the reverse potential by a few millivolts. So that is the slope with which the current increases. So there is another phenomenon known as Zener breakdown. So Zener breakdown that takes place when the potential itself you have a huge amount of potential here, and with this potential actually, on what does it depend? This potential depends on the charge concentration. If the doping concentration is not charge concentration, doping concentration, if the doping concentration is very high, so then what happens is you have large number of electrons on this side and holes on this side. Now when the junction is formed, so they diffuse, so naturally the diffused charge would be very large, and when the diffused charge is very large, you have a huge amount of junction potential, so that would be forming across the junction. And this junction potential causes avalanche breakdown as well, as I have already explained. When the holes go down this potential, go down this region, this junction region, so they get accelerated and they bombard the charged particles. On the other hand, this field itself may be large enough to expel electrons from the covalent bonds. Okay? If the field itself is very large and the potential is much larger than the band gap, the valence electrons may get out of the covalent bonds and available as free electrons. It's not because of bombardment by the minority carriers, but it is because of the huge amount of field that is available here through the junction charge, as well as which is partially caused by the external strong reverse potential. Please note that the junction voltage is not only due to the diffusion of the charged particles, it is also due to the reverse potential that is applied across this. So because of this reason, the covalent bonds are broken and huge number of 4 electron pairs occur, and these whole electron pairs contributes for huge current, and as a result you have the Zener breaking down taking place, and the characteristics would be something like this. Well, whether it is avalanche breakdown or Zener breakdown which occurs in a particular diode depends on the concentration of the doping concentration. If the doping concentration is very large, naturally it is a Zener breakdown, so that occurs in a diode. I forgot mentioning one point earlier when I discussed about the volt ampere characteristics of a diode. Please look at this diagram. I said this current is equal to the reverse saturation current. Now how much is this reverse saturation current? It is of the order of a nanoampere in the case of silicon diodes, and it is of the order of a microampere in the case of germanium. So this is the reason why with the low voltage itself germanium gives rise to appreciable amount of current, whereas in the case of silicon it needs a little higher voltage than in the germanium case to give a high amount of current. Now this is the characteristics of a PN junction diode, and the symbol used for a PN junction diode is like this. This is the symbol, where this is the P side and this is the N side. Now when you use this diode in some applications, how does it behave? It behaves in this way. The volt ampere characteristics is the characteristics you look for. So this gives the characteristics of the diode. Well, if you apply some positive potential, it allows the current to take place, and if you apply some negative potential across it, it doesn't allow the current to pass through, appreciable amount of current to pass through up to certain voltage, and of course beyond that it allows the current to pass through. Okay, so we'll continue this class in the next period.